The second talk of the afternoon, we have Seung-Joo Lee, who's going to tell us about physics and geometry of open string limits. Thank you.
Thank you. So I'd like to start by thanking the organizer for kindly inviting me to speak here and for putting together such a nice conference. So today I'll talk about physics and geometry of open string limits, and I'll address both strings and geometry. Specifically, I'll be focusing mainly on, F theory, for which the geometry will amount to elliptic Calabi-Yau varieties. So this talk will be based on these papers done in collaboration with my wonderful collaborators, all in the audience, Wolfgang Liehe at CERN, and Timo Weigand and Rafael Alvarez-Garcia here at Hamburg, our organizers. So let me start with some motivation. So in this talk, we will analyze the string vector obtained via geometric compactifications on Calabi-Yau manifolds. So what we know about their explicit geometric construction, a particularly useful way to construct them is to carve them out in a simple ambient space as the zero locus of polynomials, or more generally of the global homomorphic sections. And this way, a big data set arises of over 1 billion already for treefolds. In fact, this number is an extremely conservative estimate because it only counts reflexive polytopes, each leading to multiple different Calabi-Yau treefolds generically. And as for the actual Calabi-Yau counting, we expect an order of 10 to the hundreds, which is a very huge number. And interestingly, a majority of these manifolds are elliptic fibrations, and this could as well be an artifact of this particular construction, but it's still interesting and perhaps also surprising. So two lessons here. A, there exists a vast number of different Calabi-Yau manifolds, and B, it may not be too much of a restriction if we only consider the elliptic ones. Now, quantum gravity theory in the UV is highly constrained and reflected by the uniqueness of string theory. Nevertheless, due already to the multitude of the allowed internal manifolds, there arises a plethora of string EFTs at low energy, and this huge set of string EFTs is known as the string landscape. And of course, there are a lot of EFTs beyond the string landscape too, and by collecting all those EFTs that have a UV completion into quantum gravity, we can form a full landscape, which by construction contains a string landscape. And those EFTs without a UV completion define the Swampland. And the Swampland program aims to distinguish the EFTs in the landscape from those in the Swampland, naturally pursuing common properties of quantum gravity theory known as quantum gravity conjectures. And the point I'd like to emphasize here is that the string landscape serves as an excellent guiding principle for the Swampland program if we can extract common properties of string EFTs. So one can try to test out some of the explicit conjectures for so many string EFTs at one go, not just for a handful of them. And if this works out, we can propose a convincing microscopic mechanism for the conjectures. And in turn, this will improve our fundamental understanding of the conjecture and eventually of quantum gravity itself. So to this end, we aim to establish appropriate universal behaviors of the internal geometry first to eventually constrain quantum gravity physics. And in principle, the string landscape could only be a proper subset of the full landscape, but even so, our spirit would arguably still be convincing given the richness of the string landscape already. So amongst a lot of conjectures in the literature, today we'll focus on the two of them, the distance and the emergent string conjectures. Both of them concern the moduli of EFTs, and for the current purpose, they concern moduli of string compactifications. So those moduli parameterize the EFTs and are encoded in the precise compactification geometries. Then the two conjectures characterize universal behaviors of the EFTs at infinite distance in the moduli space. Now, the distance conjecture claims that a tower of physical states become light at infinite distance in this exponential fashion. And this conjecture, it turns out, is applicable to a wide range of these phenomena with many interesting consequences, and its validity has been confirmed in various string setups. Even so, it still remains a conjecture, and to develop proper intuitions, it's important to reveal the very physical nature or the origin of the light hour states predicted at infinite distance. And along this line, the emergent string conjecture claims that at infinite distance, the EFT either decompactifies or reduces to a weakly coupled tensional string theory. And this conjecture refines the distance conjecture in that the former case leads to a light tower of Kaluza-Klein states, and the latter to a light tower of string excitation states. And strong evidence arises from non-trivial string setups at infinite distance in the moduli space, both for Kähler and the complex structure limits. As for the Kähler or the size limits, the possibility of decompactification is perhaps natural, but the emergence of a unique critical tensional string is not as obvious. This has nevertheless been carefully addressed in FM and type 2 theories on Calabi-Yau threefolds, M theory on G2 submanifolds, and also in four-dimensional F theory with minimal supersymmetry. And as for the complex structure of the shape limits, it's sometimes difficult to observe decompactifications. But success stories have still come out starting from the type 2 setup. And the way these string setups realize the conjecture relies heavily on many interesting and non-trivial results in algebraic geometry, sometimes rather intricate, but it just works out eventually. So one may think that the conjecture is pretty convincing, at least from this top-down perspective. Apparently, however, all of this concerns the closed string limits, so it's much desirable and also timely to analyze the open string limits to also better understand this conjecture and even challenge it in this qualitatively different setting. And in this regard, what's particularly nice about F theory is that its open string moduli are part of the Calabi-Yau complex structure, so we can still exploit the power of the bulk geometry, so to speak, and this is what I will address in this talk. So let me first give some rudiments to set the scene up. So our arena is F theory, about which we've already heard a lot, but let me still try to be self-consistent. So we compactify type 2B string theory on a default B hat, which leads to a string EFT in 10-2D dimensions, real dimensions. And here, the internal space B hat has stacks of 7 rains on its divisors. They source a dilaton profile and carry gauge fields valued in real algebra G. And as for the geometry, we consider an elliptic fibration Y hat over B hat, where the dilaton value at each point of B hat is identified with the complex structure of the elliptic fiber. And the total space Y hat is Calabi-Yau for it to define a string vacuum. And here the 7 rain stacks are located on the components of the discriminants supporting singular fibers, and the fiber singularities on the brane loci, which are codimension 1 loci in the base, encode the Dynkin diagram of G. And let me explain this connection better by setting D to 1 for concreteness. So for now, Y hat will be a K3 surface and B hat a rational curve. In fact, our Y hat is a Weierstrass model defined over the base P1 with homogeneous coordinate ST. And for the total space to be Calabi-Yau here, F and G are to be of degrees 8 and 12, so the discriminant, now I call it delta, has 24 zeros, and these are the locations where the singular fibers are supported, and also the 7 branes are located in the internal space. And therefore, the fiber part of the complex structure controls the 7 brane configurations of which limit we will analyze. Famously, the singular fibers are classified via the vanishing orders of Fg and delta to various data, and this table lists the so-called minimal codiator fibers. So such fibers over codimension 1 loci in the base encode the gauge algebras of a Lie type. They're known to arise at finite distance. However, the classification should not stop here, because already degree-wise, the vanishing order triples can easily go beyond 4, 6, and 12 at a time, which were missing from the previous table. And such badly singular fibers and the corresponding 7 brane stacks are both called non-minimal. Now, the models involving such codimension 1 non-minimality are typically discarded in the literature well, partly because they lack a crepant resolution, rendering the physical interpretation obscure. However, such models do exist. You can just write them down, and they call for a proper analysis systematically. Now, the minimal fibers are sitting at finite distance, and naturally, one might guess that these non-minimal fibers are at infinite distance. And the other candidate for an infinite distance limit is to have codimension 0 singular fibers. And the questions arise, are these really of infinite distance, not just potentially, and what are their physics? And it turns out that we can address these questions by modifying the degenerate Weierstrass model to a so-called Kulikov model. So what is a Kulikov model? So here we consider degeneration of K3 surface, elliptic or not, generally, defined as a family of surfaces XU. So generically, XU is a smooth K3, but the central element X0 can decompose into several components, X upper i's. Then the degeneration is called a Kulikov model if it exhibits good properties for singularity and for minimality. And it's known that every K3 degeneration can be turned into a Kulikov model via these natural operations in birational geometry, the base changes and blow-ups and downs. But this is only for the existence. And in this talk, I'll be explaining how to actually get to Kulikov models without affecting the physics. And I will also clarify the characteristic geometry in connection with universal physics. In fact, the Kulikov models had already been nicely classified into 3 types. So type 1 is a finite distance, so the standard Lie-type degenerations should belong to this. But today we are more interested in type 2 and 3 at infinite distance. So what do we know about them from the math literature? So firstly, in type 2, the components of the central K3, the X upper i's, arranged in this chain form, and the adjacent components intersect along an elliptic curve. And in our case, our K3 is elliptic, so we want the component xi to be also elliptic over its own base bi. And furthermore, it is known that 2 transductor 2 tori shrink in the limit. And next, in the type 3 case, I don't have a picture here, but the components can arrange in a more general fashion than this chain form, and they intersect along a rational curve instead, and only 1 2 tori shrinks in the limit. And this is the end of my rudiment. And now to the meat of this talk. Let me finally get you our main results concerning the open string limits of F theory in 8 dimensions as a starter. So summary first, what precisely have we done? Within the arena of 8-dimensional F theory, we've analyzed extreme limiting configurations of 7 rays, which amount to infinite distance fibril degenerations of a Weierstrass K3. And we arrive at their 4-fold classification, rederiving the Kulikov classification in the elliptic case, and even refining the 2 Kulikov types 2 and 3, each into 2 subtypes A and B. For this purpose, we have developed some algorithm for birational analysis, by which we can systematically modify any given degeneration with codimension 1 non-minimal fibers in order to improve the singularities and eventually to make them all minimal so that we can interpret them physically. So in this talk, I will be assuming, for simplicity of the presentation, that our initial degeneration has codimension 0 fibers smooth. Then this will lead us to the A subtypes, where the components of the central K3 take this chain form, at least at the Weierstrass level. And notably here, the genetic fibers over each of these P1 bases are of IN type, possibly with n bigger 0. So once blown up along the fiber, all the components will be reduced and normal crossing, which were the defining properties of the Kulikov model. So we see where we are going to. And also for physics, we may have a weak string coupling regime, at least locally, only locally. Now let's try to spot the vanishing cycles in these limits. For instance, in the Kulikov type 2a case. To this end, let's redraw the base components like this, and let's consider these vanishing base 1 chain sigma around this point of intersection. Then by fibering the A and the B cycles over this space 1 chain sigma, we obtain a pair of vanishing two tori as expected of Kulikov type 2. And in turn, a pair of Lie particle towers arise either from REPTEM2s or UND strings. So the EFT decompactifies from 80 to 10D. And similarly for Kulikov type 3A, I don't have text here, but we can still spot a vanishing two torus, but only one due to monodromy effect. And in the end, the EFT decompactifies this time to 90. And that's the physics of these two bottom corners. And let me just briefly mention that our birational analysis also applies even if coordination zero fibers are singular. And such limits lead us to the B subtypes. And just to state the result, their physics are string emergence and decompactification respectively. And because this is all the limits that we can consider in this elliptic case region, hence in ATF theory, we learned that every open string limit of ATF theory conforms with the emergent string conjecture, and that's the upshot. And in the next 5 minutes or so, let me elaborate on this precise birational analysis, which will lead us to these results. As it turns out, this analysis relies largely on two strategies, so I will explain these two in turn. So our degeneration, so our open string limit is degeneration curly y hat, which is a family of K-trees, elliptic in a virus form. And as I said, we will assume that the central element of this initial degeneration, y hat 0, has the generic fibers smooth. But this is some assumption for simplification, and not too important. What bothers us really is the presence of a non-minimal fiber at a point, say at s equals 0 in the P1 base. Then our strategy number one is to zoom in on this non-minimal brane stack until the constituent branes, so to speak, are separated enough. And to put geometrically, the trick is to repeatedly blow up in the base at this non-minimal locus until the non-minimality is fully improved. And these high vanishing orders at this blue point allow us to blow up the family while keeping the Calabi-Yau-Nice. So the end result of this blow up will be a modified family, curly Y, free of non-minimal fibers. And in general, one might need to blow up several times, but we can show that the blow up sequence should terminate in finite steps. So this terminates. But I'm cheating here. So I want to also say that once you fibrally blow up this curly Y, you arrive at a genuine Kulikov model, so we call it a Kulikov virus model. But as I said, I was cheating because this does not always work. This is a general spirit, but this does not always work, especially when the vanishing orders are too high. So in these first two cases, these base blowups alone do bring us to Kulikov types 2 and 3. However, in this last case, which I will call strict non-minimality for an obvious reason, this strategy does not work, just never works. So let me illustrate the success and the failure with two concrete examples now. So example number one comes with a non-minimal fiber with vanishing orders 4, 6, bigger 12. And we will arrive at a type 3 Kulikov model, which looks like this. So how do we do this? So we start by checking at s equals 0 in the original model that the FG delta vanishes to orders 4, 6, and 14. So this is non-minimal. So by blowing up at this base point, we can improve the non-minimality. In fact, for technical reason, we first perform this base change of order 3, and then we blow up 6 times. And this way we insert 6 extra P1 components to the base, and we observe that A, the 5 P1 components of the base support generic IN fibers with n bigger 0, and B, some of the components support codimension 1 singular fibers as well, but they are all coming in minimal codited type, so we are done. So this is a type 3 Kulikov model. Now the next example comes with a strictly non-minimal fiber with vanishing orders, bigger 4, bigger 6, bigger 12. And despite the presence of a non-minimal fiber, we will see that what we arrive at is actually a type 1 Kulikov model at finite distance in the moduli space. So a bit surprising, at least at first. So how do we see this? So we again start by checking at s equals 0 of the model that the vanishing order triple is 8, 12, 24, so it is indeed strictly non-minimal. Then by blowing up at this base point, we insert one extra P1 component to the base, and then we observe that the genetic fibers over this exceptional P1, they are singular. And they are not of an IN type anymore, so we already see that this cannot be a Kulikov-Weierstrass model, so they are not IN. So this failure has arisen because both the F and G orders at the initial singularity were beyond the threshold values, strictly beyond. So how do we solve this problem? The day is saved by blowing down. So in this example, we blow down the, so to speak, original component, and then we scale out the Weierstrass section F and G by appropriate powers of the degeneration parameter. We can do that in this reducible model. Then we arrive at this type 1 Kulikov model with just 24 I1 branes. So this is a finite distance in disguise. And this example already illustrates all the steps needed in generally dealing with strict non-minimal fiber. So in general, when we are given a strictly non-minimal 7-brane stack, we first apply our strategy number 1 as a starter, by which the co-dimension non-minimality is fully improved on the base chain. However, in co-dimension 0, non-IN type fibers necessarily arise on the blown up components because of the strictness of the initial non-minimality. At this stage, strategy number 2 comes in 3 steps. So firstly, we choose one base component out of the base chain appropriately. And next, we contract all other base components to make it the central K3 irreducible. And then lastly, we ensure that only IN fibers arise in co-dimension 0 by scaling out appropriately the overall factors of the parameter, the degeneration parameter. And the name of the game here is to make a right choice here in step 1 in such a way that upon blowing down all other components in step 2, we do not have any strict non-minimality in the end of the step 2. And in the paper, we carefully show that this can always be chosen in a systematic manner, the right component. And so this can always be done. And we know how to do this systematically. By combining strategy number 1 and 2, we can eventually identify the fate of this strict non-minimality as either type 1 or type 2. So what we've done here is, in the end, to extend the Kodaira-Neron classification of the minimal Kodaira fibers, which are all at finite distance, by including the co-dimension 1 non-minimal fibers as well. And therefore, given an arbitrary open string limit of ATF theory, whether at finite or at infinite distance, not only do we know how to systematically turn it into an explicit Kulikov model, but we can also read off the resulting Kulikov type and hence their characteristic physics already from the vanishing order triple, just like we do for minimal Kodaira fibers. Okay, yeah, thanks. So, indeed, so in the remaining minutes, I'd like to mention briefly how these strategies can generalize to 60F theory. Of course, novelties and complications arise in this generalized arena of 60F theory. So let's first recall that the allowed base 2 folds for elliptic Calabi-Yau 3 folds are P2, Fn, and blowups thereof. And at this initial analysis, we take the vanilla Hertzbook, forgetting about the finite distance blowups in the base. And we also assume that non-minimal loci, which are curves inside the Hertzbook, do not intersect in case there are multiple such loci. Then, given a degeneration of Weierstrass Calabi-Yau 3, we'd like to see if we can obtain a Kulikov-like Weierstrass model, essentially via base blowups and downs, which were the 2 strategies exploited in the K3 case. So, firstly, as for strategy number 1, in the K3 case, we started with a central K3 with a non-minimal fiber at a point, blue point here, and then by blowing up at this base point, we arrived at a Kulikov-Weierstrass model free of non-minimal fibers. And the Calabi-Yau 3 can be similarly treated, essentially the same, except that the non-minimal locus is now a curve inside the Hertzbook. But we can still blow up to improve the singularity, and then we arrive at a modified degeneration. So let's look at this central element more carefully. It's really the same. But now, to be more general, we can have multiple blobs in general, and then let's just align them horizontally to make it visible. Now the new base component we have to insert, they turn out to be all Hertzsprung surfaces Fk, because, as I'll justify shortly, this non-minimal locus has to be a rational curve. But this integer k, which is the self-intersection of this curve inside the original Fn, does not have to equal to the original Fn. And we can analogously classify the degenerate types into 2a and 3a with similar properties for generic singularities. So, but upshot is that strategy number 1 obviously generalizes, except that this is now a curve rather than a point. So the immediate task is then to classify the eligible curve classes that can support non-minimal singularities. So we've done this. So by noting first that the Morricone of Hertzsprung is generated by the section class H and the fiber class F with these intersection numbers, let's first give this nomenclature: the horizontal curves for sections, and the vertical for the fibers, and the mix for the rest. Then, due to these high vanishing orders required for the non-minimality, in the end, the eligible curve classes turn out to be bounded from above by the anti-canonical class. And we also want the classification to be only irreducible loci, because we want to classify the individual brane stacks. So in the end, we are left with only this handful of options, and they all turn out to be rational, except for this single elliptic case, which turn out to be trivial for physics. And this is the last slide, this is strategy number 2, on improving strict non-minimality. The complications in the Calabi-Yau 3 turn out to be severer than in the strategy number 1. So the upshot is that in the elliptic K3 case, it just worked because the geometry was much simpler. But in the Calabi-Yau 3 case, first and foremost, the base blowdowns in step 2 better not affect the chosen component. But in the Calabi-Yau 3, the base blowdowns do affect, even contract the chosen component as well, unless the non-minimal locus C is horizontal. And furthermore, at the end of step 2, even in the horizontal case, strict non-minimality may still arise on vertical or mixed curves. And the first problem is solved by flops in the end, and the second problem also solved, if you look at it, and as long as the initial degeneration is algebraic, which is the case for our limits. So let me conclude. So universal limiting behaviors of Calabi-Yau varieties may support or challenge the emergent string conjecture. And in F theory, open string limits are fibril complex structure limits and can be studied via the bulk degenerations. So for the limits of ATF theory, i.e. for elliptic K3s, we've invented a birational algorithm to modify degeneration with non-minimal fibers to Kulikov-Weierstrass models, and we've clarified the universal geometry to address the conjecture. And novelties for 60F theory, i.e. for elliptic Calabi-Yau 3s, are there, but potential problems have been resolved, and we've improved our algorithm to make it work there. And finally, this non-trivial success seems to suggest that it should generalize even to higher dimensions, and in particular to Calabi-Yau fourfolds. And I'm studying this case with the birational geometry Coulter-Birkar, and I hope that we can soon report on this as well. So thank you very much for your patience.
Thank you.